It's independent learning. Go to that chapter. What's your day been with it? So on a scale of 1 to 11.
No, I'm gonna have to start talking now. Are we gonna see how far I could go? I don't see a way of not talking. Okay. We're skipping it. We'll do it after the exam. Don't need it for the exam, so we're gonna skip it. Okay, probability. There's something called a Bernoulli trial. Now, I believe in PE, do they have something called like the Bernoulli principle or something? 51. We're skipping a bunch. This is separate to that stuff, I believe. It's the same name. So a Bernoulli trial has 3 characteristics. It's either pass or fail. Probability of success and failure do not change. And the probability, P plus Q equals 1, so probability of success plus probability of failure have to be 100%. So if you're rolling a dice, you win $5 on a 5 or 6, you lose $5 on a 1 or a 2, that would not be Bernoulli, because you have a 1/3 chance of winning, a 1/3 chance of losing, a 1/3 chance of nothing. And trials are independent, so each test doesn't affect the next. So for instance, flipping a coin is the classic example of a Bernoulli trial, because it doesn't matter what coin you just flipped, the coin doesn't remember. So when you flip another one, you're good to go.
Doesn't matter.
How do they get dice to work when they always roll it? Like the clubs?
Well, there's a lot of people that don't roll dice properly. So I know some people when you roll dice, they just put it in their hand and they just go like, but out. That won't be a fair roll. You actually force it to be whatever you want to roll.
Always.
Luck.
Just chance. Or loaded dice. So, we're going to be doing a lot about Bernoulli trials, and we'll see the link to some other things in a bit. So, show the possible outcomes of flipping a coin 1, 2, 3, or 4 times. Doing it 4 times is going to suck. But anyway. So, for A, for 1 coin flip, you can have heads or tails. For 2, you could have heads, 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 tails, tails, tails. For 3, you could have heads, 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 tails, heads, tails, heads, tails, heads, 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 tails, 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 heads, tails, 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 heads, and tails, tails, tails. I did it wrong? Oh. And that should give us 8 different possibilities. 1, 2, 3, 4, 5, 6, 7, 8. How did I know that there's going to be 8 possibilities? 2 cubed. 1 trial has 2. 2 trials has 4 because I forgot one. What one have I forgotten?
Yeah.
Tails, heads. This one will have 8. Anyone want to guess what 3 heads will have? 16. I'm not going to write them all out for this one. Oh, wait. Yeah, we want to do 4. Why did I? No, just because for the next one we're going to draw a histogram, so we're going to sort of talk about each one in depth. So 16 ways. I mean, we could sit there and list them all out, but it's kind of a waste of time. So for B, guys, we're going to draw a histogram. For our histogram, what is the least amount of heads we can have?
0.
0 heads. So we can have 0, 1 head. What's the most amount of heads we can have? We're going for 4, aren't we? Yeah. 4. Okay. So I've said there's going to be 16 ways that these can go out. How many of those ways are going to give us no heads? 1 way out of 16, because it's got to be tails, 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 tails. There's only 1 way that can happen. We're only looking at the 4 trials version. If we did a histogram for this one, it'd just be 0, 1. I don't know why that happened. 0, 1. They're even because it's 50-50 chance. For this one, 0, 1, 2. There's 1 way to get no heads, 2 ways to get 1 head, 1 way to get 2 heads, so on and so forth. For this one, what's the chance of us getting 0 heads? How many ways can we get 0 heads? 1. Out of how many ways total? 16. We're doing 4. So the probability of this one is going to be 1/16. 2 out of 16. 3 out of 16. I have not scaled this well. I'm going to cheat because I'll do 1 and 3 in a moment. How many ways are there to get 4 heads? Well, easy. Just got to look in the mirror. Haha. Sorry? No, because you have a 4 head. Yeah, you call me 4 eyes. I get it, but it doesn't fit with the context. Anyway, there's how many ways to get 4 heads when you're flipping a coin? 4 times. So if I want to get, I flip 4 and I want 4 heads. There's only 1 way for that to happen. It's got to be head, 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 head. So that would also be a 1 out of 16. What about 1 head? Any thoughts? This will have to go up to 4. So we could have head, tail, tail, tail. We could have tail, head, tail, 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 head, tail, 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 head. Those would be the 4 ways you can get 1 head. So we'd have to go up to 4 out of 16. What's going? 4 out of 16. Well, there's going to be 16. The next one is going to have more. But I'm silly. I think it's going to go up to 6. Wait, 1 plus 4. Yeah, it'll go up to 6. And I have not given myself enough room. I'll just keep it going up. If there's 4 ways to get 1 head, how many ways would there be to get 3 heads? 8. Nope. What's the difference between getting 1 head and 4 heads? Sorry, 1 head and 3 heads. Look at my list. If you just swapped the T's and the H's, you'd have the exact same thing. But this time we'd have 1 tail, 3 heads, instead of 3 heads, 1 tail. Or other way around. I'm seeing a lot of confusion. Okay, here, you see in each of these I have 1 head in those 4 ways. If I just flipped the T's and the H's, so instead of being HTTT, it was THHH. It'd still be 4 ways, and each one of those options would have 3 heads, 1 tail. So what I'm saying is getting 1 tail is going to be the same probability as getting 1 head. But I'm just expressing it in terms of heads. So getting 1 head is the same probability as getting 3 heads. Because they're the same thing going on. Now, do you reckon getting 2 heads is going to be more or less? What leads you to that conclusion? It's going up, isn't it? This is what we call a binomial distribution, and what we tend to find is they peak in the middle. So it makes sense. How many outcomes did I say there'd be? 16. We have 1 here, 1 here. 4 here, 4 here. 6 left over for the middle, because 5, 9, 10. So there's 6 left over. Let's just check that that's right. So how many ways could we have 2 heads, 2 tails? We could have head, head, tails, tails. Head, tails, head, tails. Head, tail, tail, head. And then we're just going to do the exact same thing. We'll flip it. All the heads and tails. We could have tail, tail, head, head, tail, head, tail, head. Yeah, well, that's what I meant. We're not going to list them there because we're going to do it again down here. So I just didn't want to repeat what. Tail, head, head, tails. Is there any other way to get 2 heads, 2 tails that I haven't listed there that you can think of? There shouldn't be, with our understanding of maths being what it is. So that one would go up to, that would have a 6 out of 16 chance of happening. Okay. Very, very fascinating, right? This is what you come to learn about. I had so much extra room too. I could have just drawn it completely. This is what you get. Okay. So Bernoulli outputs a binomial probability distribution. This lets us know how many successes to expect when performing multiple Bernoulli trials. So each coin flip is a unique trial. So if I said, for instance, I'm going to flip 5,000 coins, you should expect 2,500 heads, right? Because it'll be 50-50, assuming it's a fair coin. In the casino, they basically do this. Because in the casino, they shuffle their cards between each round, and they are trying to make sure that they know the likelihood of how much they're winning. Because then if they expect to lose every 3 games and win they lose 3 games for every 4 they win, for instance, and make sure they can balance their payouts so that statistically they come out on top. Does that make sense? So this is the field of maths that's around planning, essentially, accounting for randomness. Well, not so much this, but no, if you got really good at this, you wouldn't be at work. You'd be one of the people that are not working on the floor, but you're setting up the new games and stuff, and they get paid really, really well. This kind of stuff is. They don't. There are people that do things like count cards. Well, casino is. There's 2 different types of games, right? And this is so related to what we're doing, but I'll explain it anyway. There's 2 different types of games. There's the ones where you're against the house. So the casino, you're playing against the casino. So if you win, there's generally standard odds. So if you play blackjack, for instance, that's against the casino. And I don't know. I don't go to the casino. That doesn't shock me. But if you go and pay blackjack, they match whatever you've bet. So there's a 1-to-1 win-loss thing. But the thing is, yeah, so if you've bet $50 that you're going to beat the dealer and you win, you get $100. If you lose your $50. So they match your bet.
And if match the dealer gets a good push, they actually whatever.
Yeah, right. I don't play blackjack. But yeah, I didn't know you could do that. Where was I going with this? So what they do, because it's even, if that was just like if it was fair for both the player and the house and the bets are matched, that means that after 1 million games, the casino will have expected to make $0 because it's a fair game. But if they make what the casinos do is they make the game skewed enough so that they make a profit, but also so the player wins enough that they feel like they're doing well. So they might win the house might win 55% of games instead of 50%. So on average, they will end up on top. You don't get rich playing against the casino unless you happen to like. The only way you can get rich playing at the casino is if you go in and slap, 10 grand down on the table and be like, okay, I'm doing a roulette spin or I'm doing whatever. I've also heard stories of walking in betting $50,000 on like red and black comes up and they've just lost $50,000. So that is where this stuff comes in because the casino has done all this math behind the scenes to make sure that they know exactly what to expect on their game. The other type of game, so that's against the house. The other type of game is like poker, where you're playing against other people. So when you play poker, the house, so the casino, the house, you're not playing against them. You're playing against the other people at the table. So you're not taking money from the casino. You're taking money from the other people at the table, or they are taking money off you. So there are people that are like the people that you can watch like on ESPN and stuff, poker games. Because the people at the top of like playing poker, they know like the percentage likelihood of winning with every hand. So if you have like a pair of kings in your hand, and you've got like the queen and the, I don't know, a 10 and 5 in the center, really good poker players look at what's in their hand, look at what's there, and they can say, okay, I have a 3.8% chance of having the best hand. And then they look at what everyone around them does. So let's say Tyson looks at his cards and he folds. Sajith looks at his cards and he raises the bet $100. So then me knowing I have my 3.8% chance, I'm like, okay, do I think Sajith is bluffing? Or do I think he has a really good hand? Whatever. And that's what the pro poker players do there. Yeah.
I can say. You know what?
What do you mean?
You play games that.
So when you're playing against the house, so for instance, blackjack, the game is just set up so that the casino has a higher chance of winning than you do.
Yeah.
You play against the dealer. So, for instance, in blackjack, the dealer, everyone that's playing gets dealt 2 cards, and the dealer gets dealt 2 cards. And the way you win a hand of blackjack is either you get blackjack and you automatically win, I'm pretty sure. So if your cards add up to 21, sorry? Oh yeah, so you just get your money back. So the casino has rules for what the dealer's allowed to do. So you know how the dealer will act. So if they get like a king and a 4, so 14, the dealer has to hit that. But if the dealer's on like 16 or 17, they have to stop. So if the dealer gets 16, you have to get higher than 16, less than 21. And if you get that, you win your bet. But the thing is, the house is more likely to win because of the way they've set it up. Look, go to the casino. Like that's literally it. If you go to the casino, say, I'm going to spend $200 tonight, or I'm going to spend $300 tonight, or whatever is in your budget to spend. And if you are visiting the ATM while you're at the casino, you're doing it wrong. Like, if you walk in saying, I'm going to spend this much, like, I had, once again, so related, but I had some people I went to school with. I won't call them friends because it's like they were friends of friends sort of thing. And they got really into the casino in Brisbane, and it got to the point where they self-banned because, like, there was one guy, so he's the same age as me, his name was Jacob, and he was... I doubt he's watching Math Methods videos as a 30-year-old man. but who I literally haven't spoken to in like over a decade. But anyway, so he was going to the casino like every night playing blackjack because he like had it in his head that he was super good. And there was like a group of them that would like go really regularly to the casino. And he I forget the whole story, but he was like he had access to his girlfriend's like bank account. He was like taking money out of her bank account because he had lost all of his paycheck for the week. So he was taking money out of her bank account to try and win back, take her money, but then win extra. So he had money for the week, and then he'd like try and like sneak it back into her account. And like, they ended up getting married. I'm shocked that their relationship survived that, but I'm pretty sure they're married now. Yeah, yeah. Horses is very dodgy. Well, the jockeys as well always know. I'm gonna.
He's not wrong.
Anyway, let's talk about binomial probability distributions. We've gone a little bit away. If you want to find the probability of how many successes you have, so it's easy with coin tosses, like I said, because it's 50-50. But if you only have a 10% chance of winning or a 12% chance of winning or something, the probability, and guys, this notation is really important. I don't know why that's doing that. This notation is really important. X equals... It's doing this thing again. It's bloody annoying. The probability that X equals X. So the probability that the number of wins we want is the number of wins that happens is equal to the number of ways of obtaining X successes. So before when we looked at getting 3 heads, we had to like list out the number of ways to get the different heads. You have to know the number of different ways you can get that many successes, times by the probability of success, P, to the power of the number of wins, times the probability of failure to the power of number of trials minus X successes. So for instance, getting 3 heads, so flipping a coin 3 times and getting 2 heads would be, there's 2 ways to get that. So the probability that X equals 2, so 2 heads, would be the number of way of getting 2 heads. There's 2 different ways. Heads, heads, tail. Sorry, there's 3 different ways. Heads, heads, tails, heads, tails, heads, tails, heads, heads. Times by the probability of success, a half, to the power of the number of successes, 2, times by the probability of failure, 1/2, to the number of trials, 3. Well, flipping a coin, it would be, Q is the probability of failure. Flipping a coin, if probability of success is heads, probability of failure is tails, so a half to the 1, because that would be 3 minus 2 successes. And that would give us the probability of getting exactly 2. So that would be a quarter times a half and 8. 3/8, which is what we found when we manually listed out every single possible answer. There's another way to do it. We don't really use this one anymore. I just kept it in there as an artifact. In the old Math B curriculum, students used to have a copy of this table. And it's how you maybe it is in your textbook. Or maybe that's the old Math B one. Anyway, if you have 5 trials, your chance of success is 0.4, and you want 3 victories, 3 successes, the probability of that is 0.23. So you just look for how many trials, how many successes, what the chance of success is. So you just read the table, basically. Pretty easy. So if I did a Bernoulli trial 7 times, I want 6 successes and a probability of 0.3 of success. It's that highlighted one there, 0.004. So I have a 0.4% chance of getting 6 out of 7 successes if the chance of success is 0.3. Which makes sense. If you only have a 30% chance of it happening, having it happen 6 out of 7 times is very, 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 very unlikely. How many times would you expect something with a 30% chance of happening? If you did 7 trials, what would you expect? Like maybe 2 or 3 out of 7 would be most likely. Yeah. Does that make sense, guys? Yeah, let's move on. Use a table to create a probability distribution for the trial completed 4 times with a win chance of 0.5. What scenario am I describing if it's a 50% chance, 4 trials? It's basically going to be identical to what we just did before with the heads and tails, isn't it? 4 trials. So, the chance of 0 wins, 1 win, 2, 3, or 4. What is the probability of having 0 wins? 4 trials, 0 wins, win chance of 0.5. Look at your table. 4 trials, n equals 4. 0 wins, and where's my 0.5 column? 0.063. And is that the same for 4 trials? 4 trials also 0.063. How do I know, guys, that 0 and 4 are going to be the same? Will that always be the case? It's this case in this one instance for one reason, and that's because my success and failure are both 50-50. If I had a higher chance of success, my 4 would be higher than my 0. So if I had a 60% chance, it might be like 4 was like up, 2 or 3 times as high as the 0. Okay, what about 1 and 3? What's my probability for those?
4, 0.5. 250, 250.25.
Say again. So 2.25, 0.25. Which should be about there. And then for 2, 0.375. Which is 3 out of 8, or 6 out of 16, which is what we found before. Questions, comments, concerns? No, makes sense. If you add them all up, they will equal 1. They might be slightly off because those have obviously been rounded, those answers, but that'd be it. Cool. Let's talk about skewed distributions. Go back to some year 9 histogram work. The best. So, in the previous section, we talked about Bernoulli trials, and we mostly looked at even chance of success, like flipping a coin. No.
Are we even going to have things in?
Not that table, no.
But X is number of decided.
Probability of X equals X, yes, we will be doing those. I think there's some practice ones in the textbook that I've given you to do. Didn't want to. Don't question my methods, Cody. They're mysterious and elusive. So, we talked about Bernoulli trials looking at even events, but most Bernoulli trials are lopsided. So, for instance, you could say a Bernoulli trial. Has anyone tried to drive north of town recently? So they've got the bridge over the Don is
60.
It's one lane at the moment. There's a traffic light set up there. So you could say success is driving up to the bridge and you have the green light. Failure is you have the red light. Would it be 50-50? Might be. It might be. You'd assume, but there might be more traffic going in one direction at different times of the day, maybe. So
Or
in the morning, or do that. But you could say that in the morning there might be more traffic going north like people leaving Bowen, then people coming into Bowen, for instance. So you might say that in the mornings, the chance of hitting a red is 40%. The chance of hitting a green is 60%. So that would be a Bernoulli trial. So experiments where there's an uneven split of successes and failures will have a skewed distribution. With this distribution, guys, can you see that the probability of success is 0.2? So does it make sense that it's skewed to the left, a low amount of successes? Because you have a high chance of failing. If you have a look, if you do, 15 trials with a 20% chance of success, would you expect there to be a likelihood of getting 15 out of 15? If that, I mean, theoretically it's possible, but it would be very, 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 very low. Well under 1% chance. The flip side of that then is with a 0.8, it's basically a mirror image. Really high chance of wins, low chance of failures. There is a very low chance of getting no wins, low chance of getting 1, 2, 3, or 4 wins. We can actually start seeing on the graph the chance of getting 5 wins. So that's like maybe 1-ish%, 0.5% around there. And then in the middle, on the right rather, we have an even chance, a 0.5%, a 0.5, so a 50-50 split of wins and losses. And you can see that gives us a symmetrical distribution there. We are going to be using these distributions quite a lot. Okay, we're setting up so many things, guys. Standard deviation and mean. So the expected value of x is the number of trials times the probability of success. Pretty basic. If I have a 10% chance of winning and I do 100 tries, I'll expect to win 10 out of 100. Makes sense. Find the mean of the following. So the only thing worth noting here is EX means mean or the expected value. So the expected value of X equals N times P. Flipping heads is a half. 15 heads is what I would expect. Pretty basic. Drawing a card with replacement where success is not getting a heart. How many trials am I doing? What's the probability of not getting a heart out of a deck of cards? Or how many suits are there? 4 suits. Not getting a heart leaves 3 suits left over. 3 out of 4. 3/4 of 100 is 75 wins. 75 successes. Rolling 2 dice and getting snake eyes with 73 attempts. I know this because I'm a nerd, but when you roll 2 dice, the chance of any particular 2, there's 36 ways the numbers can show up. You can get a 1 and 6 other numbers, a 2 and 6 other numbers, 3 and 6 other numbers, blah, blah, blah. So the chance of getting double 1s would be 1 out of 36. So the expected number of snake eyes... Oh, by the way, snake eyes means 2 1s. Yeah.
Snake.
Okay.
Yeah.
So you have to do that in your calculator, guys, but I expect it to be about 1 and a bit. Oh, sorry, 2 and a bit. 2 point something, something, something.
License.
73 attempts. Because that's not the way life works.
Like you do a chapter basic.
Like I said, Cody, my ways are mysterious. Does anyone have... I could put multiplication facts on here as well, but I'm not doing that either. What's our number? Can someone do that in the calculator for me? Yeah, we'll round it off there. That's plenty. Okay. Have you guys done in science at all standard deviation? Okay, standard deviation is just a measure of how far your data spreads from the mean. 90% of data is within 2 standard deviations of the mean. So that means 2 above or 2 below. So if someone says like you're 3 standard deviations above the mean, that means you're exceptional in that category. Because 95% of people are within 2 either side. If someone says you're like 2.5 standard deviations below the mean, that means you suck pretty bad. So this is our rule. Standard deviation is root NPQ. Calculate the standard deviation of these. Flipping heads on 30 trials. Standard deviation of x equals root NPQ. 30 times a half times a half. You guys are going to have to tell me what that's equal to. Shouldn't be that low. So what that means, guys, is what would be the mean number of heads when you're flipping coins? How many coins would you expect to get when you're flipping coins? 30 trials. Yeah, so expect 15. Um, 95% will be 15 plus or minus 2 times 2.73. So what I mean by that is if you did a gazillion flips of heads, sorry, let me rephrase that. I don't want to do that. So if 95% of the time when I do my 30 trials, flip 30 coins, that's what I do in my spare time. 95% of the time, 2.73 times 2 is about 5. So 95% of the time, I'll get between 10 and 20 heads. It's going to be very rare that I get below 20. It's going to be very rare that I get above 20, below 10. The number of heads I get 2 times the standard deviation. So am I talking gibberish here, or does that kind of make sense? Because we did that in the previous question. The expected value of doing 30 heads. So that's not a rule. That's not a rule. It's just that up here, I said approximately 95% of data will be within 2 standard deviations of the mean value. We know from the previous question, you would expect to have 15 heads out of 30. That's what we expect to get. We know that experimental data in real life doesn't happen. But we do know that for something like that, 95% of data is within 2 standard deviations. So if I figure out what the mean plus 2 standard deviations is, the mean minus 2 standard deviations, that's the limit that 95% of my data would be in. So if I flip 30 coins, it's highly random how many heads I get. But I would be shocked if I got less than 10 heads. I'd also be shocked if I got more than 20, because that's only going to happen 5% of the time.
Yeah, it ranges from 20.48 to 9.52. Would be your most of it.
Okay, let's find the standard deviation of drawing a card where success is not getting a heart after 100 trials. So we're doing 100 trials. Success is getting a diamond, a club, or a spade. And we're trying to figure out what the standard deviation is. Now, we found the mean before was 75 wins. So we're going to say if this is our game, we can know 95% of the time it's going to be between two different values where the middle of them is going to be 75. So our standard deviation, root NPQ, 100 times 3/4 times 1/4. What's that give us? So I'll have to do that in the calculator. Tyson's on it.
Where do you get the fraction part from? Like the 3 or 4?
Because so the chance of success is 3/4 after 4. What do we get? 18.75. Why is Mr. Ross in a crocodile onesie?
You missed it. You should have been right on death.
Okay, we've got root. Root 100 times 4.33, which makes a lot more sense. Okay, and I'm going to skip that. Guys, you can have a look. I skipped C. I don't care about it. Cody was whinging too much before this. I'm a ban. Alright, whatever.
It's 2048 levels. Alright, so you know the game. 2048 is an important number somehow. What is 2048?
Oh, that's just a high power of 2.
Yeah.
So just 2 times 2 times 2 enough times. Maybe. Put that in your calculator, get an answer. Then have you got page 183, exercise 5.3.